Assalamualaikum warahmatullahi wabarakatuh. Okay, first of all, we from Group 5, we want to thank our lecturer for PHY 533, which is lecturer Madam Roshani binti Afendi Azaman, for giving us this opportunity to present about the topic of Euler's equation of motion of a rigid body. Okay, first of all, we want to introduce our team members. Okay, next slide. Okay, this is the list of our team members, which is the first one is Awis Al-Qarni bin Fakrul Razi. The second one is Azri Haikal bin Azami. The third one is Muhammad Adib bin Kamal. The fourth one is Muhammad Zulharmi Takzim bin Kamur Zaman. And the last one is Ruzaiman bin Muzani. Okay, this is the table of content for our topic, which is the first one is introduction. The second one is application. And the last one, we will conduct a Q&A session. Okay, next. Okay, for the introduction, I will pass this session to our team members, which is Azri Haikal.
Okay, for the introduction, what is Euler equation? Euler equation is an equation that can be used to describe how a rigid body rotates around its main axis. Anytime an object rotates around any axis, the position of those axes within the object also change. Okay, now we know what is Euler equation, and now let's see the step for the obtaining the equations. Okay, in Euler equation, we usually refer to two different coordinate systems, which are a space frame, or also called as a fixed frame, and other frame is called the body frames or rotated frame. Okay, first equation is derivative of angular momentum with respect to time, and is applied torques. Since we have two different frames, which are fixed frame and rotating frame, the next equation show the relationship between those two frames. Derivative of angular momentum with respect to time in a fixed frame is equal to derivative of angular momentum with respect to time in rotating frame plus omega cross L, because the rotated frame itself is rotating. Since derivative of angular momentum with respect to time in a fixed frame is equal to n's or torques, we can change that to the n's. Okay, for the third equation, we need to take note of these equations. From the equation omega cross L, we need the latter equation to turn into a cross product determinants. From the cross product determinants, we need to enter or substitute value from cross product and the third step equation into the second step equation in a metric form into three components, which is Euler equation of rigid body motions. From the last equation, we can see there is the Euler equation of rigid body motion. Okay, that's all for the step equation.
Okay, now for the next session, we will move to the application of Euler's equation of motion as a rigid body in our daily life. Okay, for the next session, I will pass to the next team member, which is Awis Al-Qarni.
Okay, the application of Euler's equation of motion. For this session, I will conduct it. Okay, Zul, can we go to the next slide? Okay, first example of the Euler equation of rigid body motion was a gyroscope. Okay, next slide, Zul. Okay, gyroscope are another example for the motion rigid body in our daily life. Gyroscope is an object that is often used in airplane to make sure their navigation does not hit anything on the ground and prevent them from crashing. Gyroscope will spin in a circle and create a force that will make it turn to its original place. The force that is created with the gyroscope has an effect called precession. It will stay in that position as long as the force is applied to it. When the force is applied, the section of the top of the gyroscope will try to move to the left, and the section of the bottom of the gyroscope will try to move to the right. Okay, so next slide. So the top point of the gyroscope is acted on by the force applied and begins to move toward the left. It continues trying to move leftward because Newton's first law, like the gyro spinning, rotates it. This force rotates the wheel in the precession direction as the identified point continues to rotate 90 more degrees. The original motion are cancelled, so the gyroscope hang in the air. Application occurs. Okay, that's for the first example. Now we move to Zulharmi Takzim for the second example.
Thank you, Awis. So next slide is example 2 is fidget spinner. Next slide. In general, a fidget spinner is a stress and anxiety management toy that has a ball bearing mechanism attached to its center, and plastic or metallic frame that conceal the internal mechanical design of the toy. Fidget spinner is a good example of for motion as a rigid body in daily life. Before fidget spinner spin, we need our force from our finger to fidget spinner rotate. The spinner continue to spin as long as the kinetic energy it has generated is not totally used up. This indicates that until an external twisted force or torque act against the spinning toy, its angular momentum will stay conserved. In this situation, air resistance, also known as drag force or mechanical force, can serve as illustration of the outside force that could interfere with the toy behavior and cause it to rotate or spin unevenly. The fidget spinner spin indefinitely in perfect setting with no danger or air resistance or any other external force acting on the toy. Next slide. So the direction of large angular momentum can be identified by using the right hand rule. After that, we try to move our twist. Our twist will feel weird in our hand. There is resistance when the wrist want to turn and it feel like exerting some movement to make it not turn. Because of that, to maintain the movement of the fidget spinner, the wrist must apart. Then we need use you need use formula omega cross h equal to find L to find out the movement which that need to be apart to maintain the movement. That's all for me. Thank you.
Okay, next we move to the problem and solution. In this part, we took past year question, July 2017, which is question 4. This is the question. First, question A, derive Euler equation of motion of a rigid body. So let's go, we take a look at the solution. First, referring to the theory of rotating coordinate system developed in chapter 5, we know that the time rate of change of the angular momentum vector in a fixed inertial system versus a rotating system is given by the formula. You can refer equation chapter 5. The equation is same as the equation of the Euler equation, which is dl over dt fixed frame equal to dl over dt rotation plus omega cross L. Then we get the n. Thus the equation of motion, the rotating system is n equal to dl over dt rotation plus omega cross L. Next, as we know, dl over dt rotation equal to L dot equal to I omega dot equal to this metric. I omega dot 1, I2 omega dot 2, I3 omega dot 3. So as Azri said that the cross product between omega cross L equal to omega cross L is the I dot omega. Then we obtain the determinant as shown. Next, we do the cross product between them and then we got this equation. Next we obtain the Euler equation, which is n1, n2, n3 in the metric form equal to the I dot omega, I1 dot omega 1, I2 dot omega 2, I3 dot omega 3 plus omega 2, omega 3, bracket I3 minus I2 and as follows. Next, we go to the question 2, B. Determine the net torque and of a rigid body as it rotates about a fixed axis with constant angular velocity. As the first application of Euler equation, we take up a special case of a rigid body that is constrained to the rotated about a fixed axis with constant angular velocity. Then we know that constant angular velocity is equal to 0. Omega dot 1 equal to omega dot 2 equal to omega dot 3 equal to 0 because it is a fixed axis. Next, we cancel. Next, the Euler equation reduced to the n1, n2, n3 equal to the we cancel the I1 dot omega dot 1, I2 omega dot 2, I3 omega dot 3 because the fixed frame equal to 0. Next, C. Show the oscillation in the simple harmonic motion by using the Lagrange equation. For your information, this is not our our part, but this is in the equation 4, and then we just show to you as the extra part. So L equal to T minus V equal to this equation as shown in C. If X is the displacement coordinate, show that acceleration is in a simple harmonic motion by using one Lagrange equation, two Hamilton equation. In this equation, they want you to show that F equal to negative kx. You just derive the equation, and as shown in this slide. You just show that F equal to negative kx, same as the Hamilton equation. I think that's all from me. Thank you.
Okay, thank you, Adib. Okay, now we move to a Q&A session. So if anyone want to ask a question, feel free to ask.
Yes, I have a question to ask. Can I know what is the weakness of Euler equation of motion for a rigid body?
Okay, thank you for the question, Hifzan. Okay. Okay, first of all, in Euler's equation of motion, the angular velocity of the rigid body should be the same with the angular velocity of the system. When we talk about a body that is rotating, we can relate it with torque, which is torque is a force that causes the rotation of the body. Okay, in Euler's equation of the motion, the external torques are obtained from a body fixed frame, and we already know the orientation of the body. But for a non-zero torques, the problem cannot be solved until we know the exact orientation of the body. Okay, however, this problem will be disappear if the external torques are zero or if a motion of body is already known. Okay, both of these, which is zero external torques or a motion of body is already known, both of these is required to make the calculation about the torques that was needed to make a motion of body is happen. Okay, I think that's answer the question.
Yes, thank you.
Okay. Okay, anyone? Any more question want to ask?
I want to ask a question. Did the motion of an object is dependent on the structure of the body?
Oh, okay, thank you for the question. The question asks about did a motion of an object is dependent on the structure of the body? Okay, actually, the motion of rigid body is depends on the structure of body through the three principal movement of inertia, which is I1, I2, and I3. Okay, if all bodies have the same principal movement of inertia, it will behave exactly the same, even though the body may have a different shape. Okay, the simplest geometrical shape of a body having a three different principal movement is a homogeneous ellipsoid. So the rigid body motion often is stated in terms of the equivalent ellipsoid that has the same principal movements. That's answer the question. Is that answer the question?
Thank you.
Okay, if no more question, I think I want to conclude our presentation. Okay, for a conclusion for this topic, Euler's equation of motion is an equation that was used to know how actually rigid body was rotating around its axis. There were many applications of Euler's equation of motion of a rigid body that can be related in our daily life. As we discussed earlier, the applications such as a gyroscope and a fidget spinner are some of the other many applications that was used in our daily life. If there is no gyroscope application, maybe today we cannot see an airplane can fly perfectly. So we as a student, we should learn more and implement it in our daily life. Okay, I think that's all for our presentation for this topic. Okay, I want to thank all the audience that give that ask a question about this topic. Okay, I think that's all from us, Group 5. Thank you. Thank you all for participating in this presentation.